Hi guys, let's try to do the Leetcode 701 today. Insert into a binary search tree. It has been characterized as medium. I wonder why did they characterize this as medium? Because if you have to insert the binary search trees, they have their own typical patterns. And if you know the pattern, it could be considered a very easy problem. And if you do not, it could be a little bit serious problem. So I would say that, well, if they have characterized this is their problem, we have to go and solve this. Now, given the root node of a binary search tree and a value to be inserted into the tree, insert the value in the BST, return the root node of the BST after the insertion. It is guaranteed that the new value does not exist in the original BST. Note that there may exist multiple valid ways for the good thing here is that we don't have duplicates in the BST. It's a real true BST in the sense that it follows the properties of the BST, that everything on its left is less than everything on its right of the root. So note that there may exist multiple valid ways for the insertion as long as the tree remains a BST. That's the good one here, right? You can return any of them. So he has this tree here, and he says that suppose we have to insert 5. As you can see, 5 is more than the 4, the root node 4, so it goes to the right, and then goes to 7. Now 7 is as you can see, the 4 is actually, yeah, so 5 is more, so it goes, but 5 but 7 uh, uh, is but 5 is less than 7. 5 is more than 4, so it goes to the right, but 5 is less than 7, so it goes to the left. So you go right from the root and then you go left, so it would end up being over here at 5, as you can see. If you had to insert a node like 9 here, it would go right because 9 is more than the root, but then at 7 it will decide that 9 is still higher than that 7, so it will go to the right, so you will end up having 5 7 and then here 9. But then he says that you could also have done something like that, in the sense that as long as the BST property is held, it doesn't matter that you just basically only have one way to solve this problem. You can always rearrange, and I think this is going to be harder because I, I have probably not yet solved problems related where we can rearrange the BST, in the sense that we in this case, you see, he actually just changed the root node itself. It's no longer 4. Now the constraints as the number of nodes in the given tree will be between 0 and 10,000. Each node will have a unique integer value from 0 to 10 raised to the power 8 inclusive. So the values are going to be between this range. I wonder how is that relevant, or how we can make sense of that. Does it really matter as long as a unique value? And the number of nodes will be between, so you're not going to have a tree with more than 10,000 nodes. The unique integer value. It's guaranteed that the well does not exist in the original BST. So let's give it a shot. We will try to do this in Python as well as in C. So let's first do Python solution. So the way it works is that you would be doing a recursive solution for this. So if root is none, then we have to basically return a tree node. Basically all we do is we just return a tree node with val as this integer. So that means this node, and then we are okay here. Now if root. Now if we see, if val greater than root dot val, then we have to go right. So we have to say insert into BST, and then we say um, we have to go right. So we just have to say here root, or we can say something like this. We can say root right equal to insert into BST root dot right and then the val. Else if val less than root dot val, then we say root dot left equal to again and then we say root dot left, and if you see here at this point we just return the original this value that we were given. Now the way the recursion works is that if you think about it, most of these here would be only time there is a malloc happening is over here, in the sense there is a new memory allocation happening. There is no malloc, this is Python, but basically where we will be allocating a new node is when we hit the leaf. Otherwise we just keep walking. So most of this code is pretty much walking, I would say, and so it can confuse people, but basically what's going to happen is you would be starting here at root, then you will go further down to the call after that, then you may have to go down to the call after this here, and this will continue until, imagine if you have only 3 level of depth stack depth, then now we will return. So suppose this one is basically now returning. So here we return. Now the caller of that guy, basically he returns here. Sorry. So this guy returns here, and then finally the original fellow, I mean our first call that we made, that returns. So this is how it's going to be basically, pretty much, folks. As you can see, we are basically, the topmost call will be the one the last to return, and then these inner depth calls will be, for example, this could be the call when we pass root as none, this one. So and then this will actually return the tree node here. Otherwise, and these other ones could be the call when we go right or left, then we basically just return whatever was passed to us. So you see, because here you see we are passing return root. Only the base case is where we actually return the new allocated node. Otherwise, we just pass the original whatever was passed to us. So as you can see, so these will just return what was passed, and only maybe this one would actually result in a real memory allocation. So let's see if it works. I'm just trying to comment this one out. This is a neat trick in Python where you can simply put something between these triple quotes, and this all is considered basically a comment kind of thing. It's kind of not compiled. It's a doc string kind of thing. So let's try to run this code, see if it works. So we have a problem because in Python you don't have else if, you have elif. So let's say elif, that's fine, that's not a big problem for us. Now we have a problem again, and he's saying insert into BST is not defined. So we have to say self dot insert dot BST. There you go. So it's accepted. Let's try to submit and see all the test cases pass, and that's pretty good news for us. We have succeeded in our efforts to solve this problem, and now we would move on to the C solution to this problem instead of Python. So as you can see, it's all looking, no pun intended, it all is all looking good. I mean, looking back, I would say this, if you have done a lot of tree related problems, this kind of pattern should be quite familiar to you. And sometimes the interviewers, what they would do, they would actually, just to make your life hard, they might say, just instead of recursive solution, let's do a iterative solution. And iterative solutions for the trees, BSTs, can be a little bit more involved than the recursive, because in recursion you just have to know the concept, but the solution itself seems fairly fairly standard kind of techniques. So as you can see here, you're just breaking it down into the smaller, and then you basically return, and then you unwrap the stack, as you can see here. So let's now try to do a C version of this problem and see if we can make a dent in that problem. So let's see. So here we are, and struct tree node. So how are we going to do this one? I mean, because we have already solved this in Python, it shouldn't be a big problem. And if you see here, what we're going to do is we will say if root is null. Sorry, I'm still used to Python. If root equal to null, this is how it should be. This is what happens when you dabble in too many languages. You keep confusing your syntax. So if root equal to null, we just say return. Now you see we have to do we have to allocate a new tree node. So maybe we need a allocate tree node function here. So let's define a new little helper function which would return the new node given the value. So that, let's call it new node, and all it does is it takes the argument on a val, and then it basically returns say. So we say we start by having a temporary pointer here, temp, and then we say temp equal to malloc size of struct node, right? And then we say temp val equal to val, and temp left equal to null, and temp right equal to null, and then we say return temp. So if root equal to null, we just say return new node with the val, and we should be we can, this is our base case basically, pretty much. Now else we say if val less than root dot val, sorry, keep confusing between Python and, if val less than root val, then we have to go to the left. So we have to say insert into BST, and then we say root left, and then we say val. Actually this should be Here it's good to keep this in mind, because it's very confusing sometimes if you have because we the it's better to do it this way, because you see, if you're really going to have this thing work here, like the left is, if root left is null, then it will go and allocate a new node here. So that's how it should be done. Else, if well greater than root well, then just this line, but change all the left pointers to the right, and it should be okay. So here we are. So here we are. So that is this, and then otherwise, when we actually fall through this, we just return the unchanged um, root pointer, return root. So with this, as you can see, apart from the leaf, when we actually come to a point where the left or the right node of the node that we were passed is null, then for that case we would end up, like, imagine if this turned out to be null here, root left, and then we pass that, and they say, then we would actually end up having this would return with a new allocated node. Otherwise you're just passing, returning back the whatever we were passed in. So again, just to keep track of the recursion, as I said in the Python solution, here in Python solution, you see here, this is basically pretty much how the recursion is going to work. You would the first call would be the last to return, and intermediate, as you can see here. So let's try if our code compiles. So all right, that's very good news for us, because we don't even have to fix any kind of syntax errors or anything. So it's working now. You see if all the test cases passed as we submit. Awesome. So that's your Leetcode 701, insert into a binary tree, and hopefully it was interesting, and let's do more of these problems in the future. We have now solved around 30 problems, but eventually we will have to get to at least hit a century. And once we hit a century, we start feeling a little bit confident to go for the interviews. And just as they say, as long as you keep your morale high, is going to be not a very tough journey. The journey is going to be easy. So the most important thing is to enjoy the journey and do not be too much focused on the destination. So with that quote, I would leave you guys to solve more problems on your own, and I will see you in the next video. Take care.